Have you ever wondered what your muscles are actually saying? Well, today we're going to plug right into the human body to understand its hidden electrical language. We're going to decode the tech that lets us listen in on our body's own control system. And trust me, what we find is pretty amazing. Think about it. Every single flex, every step, every little twitch, it's all driven by this symphony of tiny electrical signals. So what if you could actually eavesdrop on that conversation? Well, that's exactly what electromyography, or EMG for short, lets us do. It's literally the science of listening to our muscles. Now, to really wrap our heads around this, we're going to use this simple but kind of brilliant analogy. Imagine your skin is a thin wall, and your muscle, it's a party happening in the apartment right next door. Our job is to figure out what's going on at that party just by listening through the wall. This thin-walled apartment idea, it's going to be our guide for this whole explainer.
All right, so first things first. If we're trying to understand the conversation at the party, we need to know who's actually talking, right? Well, in our muscles, the speakers aren't really individuals, they're more like groups.
And this is the key concept right here, the motor unit. It's one single nerve cell, that's the motor neuron, and all the muscle fibers it's in charge of. So think of it as one group of people at the party, all chatting at the same time. You can't really pick out one person's voice, but you can definitely hear the group. And, the more groups that start talking, the louder that party gets.
So how does that group conversation actually become a sound we can record? Well, it all starts with a command from the brain. That signal zips down a nerve, it hits the muscle fibers, and bam, it makes each one generate a tiny electrical spark. When all those sparks from one motor unit fire off together, they create a single, bigger electrical event. We call it a motor unit action potential, or MUAP. And that's the voice we can actually pick up from outside the wall.
So this entire journey you see here, from that first nerve impulse, all the way to a combined, recordable signal, that's the fundamental thing we're trying to capture. This is literally the sound of a muscle at work.
Okay, so we know what the conversation is, but how do we actually listen to it through the wall of our skin? Simple. We need a microphone. And in EMG, our microphones are electrodes.
So here's the basic setup. You put these electrodes on the skin, and they convert the body's electrical signals into a language that our computers can read. Just think of them as super sensitive ears pressed right up against that thin apartment wall, trying to hear the party next door.
But, there's a catch. The very act of listening can sometimes mess with what you're trying to hear. It's a thing called loading down the circuit. Basically, if our microphone, the amplifier, draws too much energy from the source, it changes the very signal it's supposed to be measuring. It's kind of like putting a stethoscope on the wall that's so heavy it actually muffles the vibrations. So, the solution comes down to this pretty simple rule of thumb. The amplifier's input impedance, you can just think of that as its resistance to drawing power. It needs to be massive, like at least 100 times greater than the signal source. This makes sure our microphone is incredibly sensitive and doesn't distort the faint sounds coming through that wall.
Okay, so we've got our ears to the wall, we're picking up a signal, awesome. But the party next door isn't the only thing making noise, is it? There's all this background noise, and we gotta find a way to get rid of it.
Back to our analogy. The muscle signal is the specific, juicy conversation we want to analyze. But the noise, that's like the constant background music you want to ignore. The hum of the refrigerator, traffic outside. In the real world, a lot of this noise comes from the 60 hertz hum of all our electrical power lines, which our bodies just soak up like antennas. This background hum, it has a name. It's called a common mode signal. And that's because it's everywhere in the room, so it gets picked up equally by both of the electrodes we have on the skin. It's this shared, identical noise that gets mixed right in with the unique muscle conversation we're trying so hard to hear. So how in the world do you solve this? This is where the engineering gets really, really clever. It's a device called a differential amplifier. It takes the signals from two electrodes, and it only amplifies the difference between them. So since that 60 hertz background hum is identical in both signals, the amplifier just subtracts it out. It vanishes. And what are you left with? Only the unique muscle signal that's different at each electrode. It's kind of like magic. And we can clean the signal up even more. We use electronic filters that work just like a coffee filter. Seriously. They're designed to let all the good stuff, the important frequencies of the muscle signal, pass right through, while blocking other junk, like low-frequency noise, from just moving around. This gives us an even cleaner, way more usable signal to analyze. All right, we've found the conversation, we've tuned it in, and we've filtered out all the noise. Now for the payoff. What is the muscle actually saying? This is where we finally decode the message.
And here it is. This is where it all comes together. On the left, that's the raw EMG signal. It's a mess, right? It just looks chaotic, it's hard to read. But after all that processing, we get the clean waveform you see on the right. It's called a linear envelope. And suddenly, the pattern is crystal clear. We can see exactly when the muscle turns on, how hard it's working, and when it turns off. The conversation is now visible.
And this brings us to the big, so what? Why does all this matter so much? Because understanding this conversation is a game changer. It lets doctors diagnose diseases, it lets sports scientists totally optimize an athlete's performance, it helps therapists track recovery after an injury, lets engineers build mind-controlled prosthetic limbs, and it gives researchers this incredible window into how our brains command our bodies. The applications are just transformative.
By turning these faint electrical whispers into clear, actionable data, electromyography has given us something like a superpower. It's the ability to listen to our own bodies in a way we never, ever could before. It really makes you wonder. Now that we've learned the language, what other secrets are our muscles going to tell us?